So guys, we are going to discuss our next type of ADC, that is Successive Approximation ADC. We'll begin with the block diagram. First we have a comparator here whose positive terminal is connected to input voltage or analog voltage that we are supplying. Now the output of this comparator goes to control and logic circuit. Now you guys must ask, what is this? It is nothing but a combination of AND gate and a clock that we discussed in a counter type, a clock and an AND gate. It is similar to that only. Okay, now the output of this control and logic circuit goes to a register called as Successive Approximation register. Even it works similar to counter. It will increment when the clock will come to it, because the counter and registers both are made up of flip-flops. Alright, so the output will be in binary form. Let's assume we are taking 4 bits. So we have 4 bits from these lines. Now we need to convert the binary output of this register in analog form. So we use a DAC. We can use any one, either binary weighted register or R2 or ladder. Now the output from here goes back to this comparator and the comparison takes place. Okay guys, and from where do we get the output? From here. Now let's move on further. We'll discuss its working with examples. Okay, so example 1. Let's say Vin is 8 volts. Okay, now what it is, how it works. The successive approximation register sets this one to, what do I mean by that? MSB will be always be 1. If it is 3 bits, then it's going to be 1000. MSB is 1. If it's 2 bits, then it will be 10. That is, MSB is 1. So in case of 4 bits, we have 1 here. Now, its analog equivalent is 8 volts. So 8 volts will go from here, and the comparator will compare them. Now as they both are equal, the output will be 1. And now it goes back to successive approximation register. It will check that if it increments or decrements its value, the comparator will provide the output as 0. So what do we get the binary output? It is equal to 1 0 0 0. I hope you guys got this. Alright, so now let's move on to a second example. This was just a basic one. Now we are going to understand the theoretical concept and the logical concept in this type of ADC. Example 2 is, let Vin is equivalent to 14 volts. Now it is equivalent to 14 volts. Now what will happen here is, this is already 8 volts. 8 volts will go here, from here to here, and the comparison will take place. Now as Vin is greater than feedback voltage, the output is 1. Now the successive approximation register will do its task. Now what it's going to do is, here, let's say it's in the theoretical part. Now as Vin is greater than output is 1, and what successive approximation register will do is, it will keep MSB and set next bit as 1. It is logical na guys. We want the analog input to be equal to our binary input. then only we are going to get our output from here. So now from 10002 it will change to 1100. So now 14, now its analog equivalent is 12 volts again. So again this is greater, so what will happen, it will set next bit as 1, that is here. Now its equivalent, analog equivalent is equal to 14 volts. Now they both are equal. So what will happen if now it will again go back to here 1, go back to successive approximation register. Now it will check that if it increments or decrements or do any sort of change in the digital input, the output of control logic circuit will be, sorry, the output of comparator will be 0, and further the output of control logic circuit will also be 0. So there will be no change, and the binary output we will get is this one in our second example. Alright guys, so this is the theoretical part. If Vin is greater than feedback voltage. Now we are going to discuss our last example. Now guys, it's going to be a tough example. Alright, so let us say it is example 3. This example will clear all your doubts about how it works. So let Vin be 3 volts this time. Okay, now the DAC is, again DAC will provide the analog equivalent to 8 volts here. The comparison will start Vin and between 1000, that is 3 volts and 8 volts. Okay, so now we have feedback voltage greater than our analog input voltage. So what will happen? We'll discuss it in theory part. It will reset MSB and set next bit as 1. I hope you are getting this. This is logical na guys. It will try to decrement its value in order to reach to this value. Okay, so that is, it will change to 0 1 0 0. Okay, now this is equal to 4 volts. Again it is greater than this one. So what will happen? This one reset this bit. Now this one will be set to 1. Now this is equivalent to 2 volts. Is this true? No, it is not true. So now as we discussed in our example 1, if Vin is greater than feedback voltage, what happens next is, it will keep the MSB, I mean the bit we are currently in charge of, and will set next bit as 1. Now its equivalent is 3 volts. Now they both are equal. Yes guys, both are equal. What will happen here is, now the circuit will start to send 1 again to successive approximation register. Now it will check again that if it increments or decrements the value, the binary value, the output of control logic circuit and comparator will be 0. So there will be no change, and we'll get the binary output as 0011. Now as you can see, the advantage in this case, what is the advantage? The time is reduced. Right now in a counter type, we had if we have to reach a value of 16 volts, I mean 15 volts, it needs 15 clock cycles. Let's say in this example, in example 2, what we had is, in example 2, we had 14 volts. If we check this in our counter type ADC, it will need 14 clocks. It will need 14 clocks. But in this case, it needed only how much clocks? 2 clocks. Right? Because initially it was 0 0 0 0. Then it changed to this, and then it went to this, and this, sorry, it needed 3 clocks. I hope you guys are getting this. So what is the advantage? The time is reduced in this case. Now we'll discuss other types of ADCs. The next type of ADC that we are going to discuss is called as parallel type ADC. It is the fastest among all types of ADCs. Let's see this in next video. Thank you guys for watching this video.